All right. Welcome everyone to another edition of IAD's Tech Exchange Seminar Series. As you're all aware, the Tech Exchange Seminar Series is intended to showcase AI and AI adjacent activities going on campus and helping our faculty members know more about everything that's happening across different decadal units, and AI is sort of now pervasive across the campus. So today's we just have one talk. Our earlier speaker had some emergency that prevented him from talking. So, but we have an exciting talk by Dr. Baishakhi Mazumder, Associate Professor in the Department of Materials Design and Innovation. And so we'll listen to all the exciting things she has to share. Thanks.
Thank you so much. First, thank you, Ranga, for inviting me. It's a great opportunity for me to be here and know you people. As I was introduced, I'm Associate Professor in the Department of Material Design and Innovation. With the name, you can think that we also do some AI, right? And we are getting more pro and pro in this scenario in the research world. And today I will be talking about some part of my work that is very relevant to this work. So the title of my talk is Physics-Informed AI for Microscopy Data from Feature Extraction to Materials Design. So this may sound a little different than conventional AI because we use AI in different way, but I will show you how we use AI to learn the physics from a data and that we can use for design and engineering. So first to introduce my group and my lab. So we call our lab now Atomic Intelligence Lab for Materials Design because we are making our work to be more smarter way to do, not relying on ambiguity in data science. So what we do are very much focus on AI-driven multiscale microscopy for extracting physics from data, not just the characterizing the materials and getting the conventional data. Data-informed manufacturing for ultra-wide bandgap semiconductors. This is one material system that I have been focusing for decades, and we still do it with a new focus with data-driven. And we work a lot on defect control systems. Our focus is on quantum materials and ferroelectric materials for, again, different electronics and next generation devices. So this is my current team. I have a postdoctoral student and PhD student, and our lab is also supported by several federal agencies. Okay, so as we talk about that, we are going to learn physics from the material science here, right? So in material science, there are a lot of challenges because when we want to design or engineer some different system, we need to know a lot about the materials because if you want to make a device, it is not a simple system. There are heterojunction, heterointerfaces. And as an example, so we have three core area that we work. So one of them is energy. So I just take an example as a battery. So battery is made of anode, cathode, electrolyte, right? Now you can think of these are different material system. And if you pay attention if you go down from the bulk materials to really low level, it's all atomic scale phenomena. So in ideal structure, the laser is not working, I think.
It doesn't show on her.
Yeah, okay. I will just wave my hand then. So you can see the ideal structure where we want it to be, but it's never in this world, there is nothing ideal, right? So in the real structure, we have a lot of defects, and defects come from vacancies, 1D defect, 2D defect, 3D defect, like grain boundaries, segregation, all that impact the phenomena within this battery. So if you have ideal case, or if you can tune the system very well, you have a high ionic mobility in this system, which can give you, as an example, fast charging station, right? But if you don't have that, then you have low ion mobility and then slow charging thing. An example for the electronics, which is again our very major focus area, all electronics material system are made of like heterojunction. There are metals, semiconductors, insulators. There are certain specific features. It's not just like a stack. So in all that, what happens, there are interfaces. There are different material interfaces, and same in homo or hetero interfaces. There are dopings which create defects. There are heterogeneity within the same material system. And all that impacts within the material system the conductivity of the material. So it could be optoelectronics or power electronics or the grid application. So again, we are talking about really, really inside atomic level structure that can impact. Another area I would talk is quantum computing, because this is one of the fastest growing research area now. There are a lot of effort, global effort going on to make a faster quantum computing, right? But the bottleneck is coherence time. So we cannot make it longer coherence time. So if we cannot do that, we cannot have drastic speed up with the quantum computing. So basically all these systems, there are tons of examples, but I'm just focusing on these three, where it shows that everything is depending on materials itself. Because if we want a macroscopic information, we need to deal with atomic scale or like really microscopic information. So what we do now, when we want to design, we want to do like growth, characterization, then device, right? So if we know all this atomic scale phenomena, this is a huge data. Like we are dealing with complex data system. So can we really get them like smoothly to get the device design? That doesn't happen, right? So in general, when we talk about the characterization, there are many general characterization people do when they grow materials like XRD, AFM, or XPS, but all those information relies on the bulk or on the surface. As we do, oops. Oh, okay. Okay, so as we focus more on the atomic scale phenomena, because that we believe that governs the main mechanism and that will actually help us design the right device. So we always deal with, I think it's moving automatically, always deal with advanced data, which is atomic scale data. Now look at the atomic scale data that we care about. So these are the device example. The first column, which is called 2D data, transmission electron microscopy. This is an atomic scale characterization where we can see the atoms structurally. There are all these grayscale data can talk about the defects, the grain boundary, the segregation. However, it is limited with the chemical data, because it doesn't have 100% detection efficiency for all the element, and it cannot provide much of the chemical data. So then we use another advanced technique, which is atom probe tomography. It provides the three-dimensional data. So we are getting two-dimensional and three-dimensional data. Now look at the data type. This is a huge, like high-dimensional data. We collect specifically for atom probe, we collect millions of atoms. So we create like even gigabytes data. So how to deal with the data, right? So if we don't know how to deal with the data, the current and conventional characterization method lose lot of data. So although we have like a big, rich, deep data, because we are not dealing the data properly, we are losing lot of data. And finally, what we are getting is very basic information: composition, particle size, surface roughness. I mean, these are good, but these are not enough. That's the thing, because we are dealing with the atomic scale phenomena. If we want to understand that, we need to get all the information. And these techniques are actually giving us a lot of information. Only thing is we are not able to deal with the data. So understanding that, in our group, what we started doing, that first we like collect all the advanced data. So TM and APT is already advanced data, because you cannot just get the information. There are a lot of steps. However, when we generate the data, like lattice fringe patterns or diffraction patterns, phase patterns, these are giving advanced data. But look at this. This is this particular data collected billions atoms. So if we are dealing with the billion atoms in the computer itself, it is very slow and it is not collecting all the collection together. So what we wanted to do, we wanted to take help from the AI. Now, the AI is huge, right? There are so many different type of model. What to use? First thing, what we think that we have to reduce the dimension, because we have rich, like huge data, but first reducing the data, extracting the features, and then learn the features, what we have. So we use, this is not all, but these are enough to show that what we want to use to first reduce the dimension, looking at the feature extraction, and then quantifying the even extracted features. Okay. Once we can do that, now we have really rich information that we get. And based on that, now I will talk about two cases, what we are trying to do from the overall. So the first thing I want to talk about qubit structure. Like I say, quantum computing is one of the major focus nowadays, right? So globally, people are trying to make different qubit structure, like exploring lot of material system, getting like, what can give the longest coherence time. So if we look at the quantum computer, the main thing here is the quantum processor, where qubit is the basis of that quantum computing, right? Now, what is qubit? The basic component of qubit is nothing other than the two superconducting electrode separated with the insulating layer. And that, of course, is the simple structure I'm talking about, but that is there in certain layout of the device. There could be different noise level or different complication in the device design. But the main concern here is the coherence time. How to increase the coherence time, because if we cannot increase the coherence time, we cannot have like longer stability, the quantum stability, and can have the complex algorithm made for faster computing, right? And all that, so far whatever studies are there, all that depends on the TLS, which is two-level system that is generated from the material defects. Now, in this structure, you can think of material defects can be huge because there are superconducting structure. It has its own limitation. Then you have insulator. It has its own limitation. And then you have interface. So there are three levels of problem, right? So what we have done in this case, so first thing, let's talk about the good stuff that we could do. So this is in collaboration with Yale University. First time we demonstrated all nitride ALD qubit, and it's called transmon. So we already published in Nature Materials. But so this looks very promising because first of all, it's all nitride qubits. It's provide pretty much good information like the critical current, which is 1.9 picoampere for any transmon qubit can provide. So this is already good achievement. The qubit structure all looks good, but if we pay attention now in the device performance, I have boxed here. So that is the subgap area. So what is the subgap area in qubit? So you should not have any non-zero values there. It should go all the way zero values, okay? But we see some non-zero values in that larger subgap area. So this is a problem. So although it is promising, but something is going on that we are still not getting in the ideal situation, okay? Now, the first thing always we want to, so we start with the device. We grow the device, we saw the device working well, but not in the ideal condition. So then we have done the TM study, and then in TM study, first we want to see if the structure was all good, because if it is coming due to the, we know that all the device problem comes from the material structure. So when we look at the TM, this looks pretty good. Like we don't see much problem. There is a good top electrode, bottom electrode. The barrier looks not diffuse because we have worked on other qubit system where we see the diffuse barrier and lot of other issues with the chemical segregation. We don't see that. Then we see something we are missing out. Some physics is there which we are not able to understand. So we try to look at the resistance map first, and it looks like it's still uniform because for a qubit, room temperature resistance versus area is one factor to check if the qubit working well. So this is uniform. So it is not too much of the barrier problem. So what is happening then? It is, we are still missing out something. So chemical information was missing in the previous slide. So we have done atom probe data. Can you click on this figure, this one? There, yeah. Yes, yes. So this is actually three-dimensional map of the qubit. What you are seeing here with that purple dots, those are actually niobium atoms. The red one is the barrier, and again, purple, that is the niobium atoms. So the overall structure looks pretty perfect, right? You see that two electrodes and the barrier. Now this is three-dimensional. If we extracted the barrier and look here, like you are cutting the plate and looking like this, what you are seeing here, barrier chemistry, it is not homogeneous because you can see the color map. The color map is showing the composition variability, and that shows that it's not homogeneous. So if we see further the composition profile from electrode to barrier to electrode, we can see that barrier layer is nice, but we see a lot of oxygen atoms. This is the killer. So oxygen atom, generally when it is there in the device, most of the time it kills the device performance. It's not good, okay? So something is going on with the chemistry that we understand. However, we are still not able to understand where that subgap current is coming from. So as I said, these are high dimensional data. There are a lot of noise. Maybe we are missing out some latent features. So we wanted to use AI for learning something, that what we can learn from this. So when we look conventional image, this is a high resolution TM image, we can see some contrast if you see on these boxes, right? But this doesn't say much, because in TM there is a sample preparation issues, there is a thickness issues, there are artifacts because microscopy has artifacts, most of the microscopy. So we can have that. So not getting biased by just the imaging, we wanted to check the inverse fast Fourier transform patterns. So we took many slices from different region, like each region we took 15 slices, and then first we did manually, then we wanted them, because there are so many, right? We don't want user biased, so we used it automatic lining, and then we use live FFT profile. And we can clearly see there are 3 different patterns. It is supposed to be one pattern because we are trying to grow a material which should be stable phase. So one pattern should be there, but we can see there are 3 different patterns. What does it mean? So when we apply the feature extraction and clustering, we can see 3 different regions, and we can extract the number, the values for each region. We can see the values here, right? Now, theoretically, we know for these 2 different phases of niobium nitride, which was used for electrode, theoretical value is matching with the observed values, which are like phase A and phase B. And this one is the mixed phase. So what it shows, coexistence of 2 different phases, which was totally missed by the conventional characterization, because we saw TM, oh, it looks all good. We did an APT. APT doesn't give the phase, but composition. But this was missing. So what we are seeing now, that there is a co-phase existence very locally, which cannot be captured with the conventional way. So how these phases are found, because this is not enough for our curiosity. So then we did advanced analysis in APT. So in APT, we get actually atom position, and those atom position are cloud data. So basically, you can go back, extract those cloud data, and perform algorithm to get more information. So what we did, we took the detection, like detectors data, where we can see the pair separation for individual atoms. So niobium to nitrogen bond, niobium NB2 to N2 bond. And then again, we use the not to have user bias. So we use this autoencoder and the feature extraction with PC and DV scan. And we can see again 2 different type of clustering. So in this case, this is chemical data, so it's different than TM. So the output is not the same, okay? And we cannot have these values exact as the crystal structure, because in APT there is a magnification effect. We have a sample, we have a detector, so there is a lengthwise, there is a misconception. So we cannot have the exact value. However, we can have the relative value. So we knew for delta NBN phase, we have higher D value than the phase B, and that's exactly we are seeing. Now, where they are, when I say locally, right? So locally doesn't mean that it can be on the surface or the bulk, because we need to understand, that's very important, that because it is directly linked with the growth optimization, right? So we see this, then we try to map them. And when we map them, this is our substrate. So from substrate to surface, we see the epsilon phase, which is not desired, are high. As it grows, like growing further towards the surface, it is getting ideal, delta, like 2 phases are there, right? So epsilon phase is not desired, delta phase is desired. So it's more close to the substrate, but as the growth is taking longer and going forward, it is a desired phase is formed. So that means something is going on just in the beginning of the growth, right? This information cannot be achieved just by conventional characterization. So that was very powerful. And this is, again, one work we have submitted. And this is something very, very important and critical that we can't do just like that. So yeah, that helped us. And now we are optimizing the ALT growth further to have fully delta phase, which is the required. Okay. Another example, 3.5 quantum well infrared photodetector. So this has been used in the military application most of the time. It's a very complex structure because it wants to detect the infrared signal. And in the infrared signal, if we want to detect, there are certain requirements in the system. So like subband absorption so that the carrier are confined well. I'm not going too much into details here with the band gap and all. Those are the semiconductor property that is needed. But the main problem here that we want to have 3 nitride structure, and it's a complex structure because it's quantum well. That means you are dealing with thin layer of like an array of thin layer, right? So what are the challenges? The challenge will be more on the nanoscale chemistry and the interface. If we don't have that rightly done, the performance will immediately impact, okay? So growth-induced variation will impact the carrier and transport of the photodetector. So we have to understand this critically. So again, this is the ideal structure. So you can see here the boxed one where the quantum well structure is mainly here, many of them, I think it was 60. I don't remember exact the number, but 10 times of P quip. Now, again, this is a complex structure. We analyzed in advanced microscopy. It's a higher dimensional microscopy data. Now look at the structure. There are so many things going on here, right? Because these are thin layer, interfaces, composition. What about the device? Because these are microscopic scale I'm talking about, and that is macroscopic output. So macroscopic output shows the red line, which is like the device is declining. It is not performing as it's important, right? So again, so we need to understand now what is going on within the material system itself, first even before going to AI. So first thing, always we try to understand chemically. So whenever we have very thin layer interface, we definitely want to do atom probe because this is the only tool that can provide you very much chemical information at atomic scale with interface and everything. So another click here. So another thing going on here, it was P-type quip. So P-type is the doping, which is magnesium in this case. And magnesium clustering is something that TM cannot show like in general. There are other way to do it. With atom probe, we can actually determine the clustering, and it is important because these are dopants. Dopants are supposed to be substituting your lattice site so that you have the conductivity. But what it is doing, making clusters, so these are becoming inactive. You need active dopants. These are becoming inactive, and that way we cannot have conductivity as desired. So what this information we are getting here, that we have doping, those are getting clustered, so inactive sites. How many clusters and what are the shapes? That's very important. So if we have higher density, of course this is not good, and if we have, because that shows the solubility limit, but what are the shapes? Now in atom probe, again, all this information we get through our algorithm. But this algorithm cannot be accurate because everything is getting like a not sphere but ellipsoidal. But ellipsoidal clusters are theoretically not preferable. So what we are seeing is not enough information. And this is the composition information of that. So again, we are dealing with high dimensional data, although we see clustered data, but this is not enough and this is not accurate. So we have to develop something that gives more accuracy, right? So now we did advanced TM now to get some level of information from the clustering because we know that in atom probe the shapes are not ideal. This is the best thing we can do. Even with that, you can see it is hardly possible to see the clusters. It's like we can detect some of them, but not with that much proficiency. It is noisy. It is a 2D versus 3D problem because TM is a 2D data and the clusters are 3D. And this geometry is so important because how the growth can be tuned, that the geometry could be ellipsoidal, sphere, or pyramids. That is important. So then, of course, we understand that we need some more than this. So this is our workflow. From atom probe, with the algorithm, we get all this XYZ position. We get the doping information, that screening up where they are doping. We use DV scan. So this is in general we do anyways in atom probe. Now we have the cluster determination. Now we define our feature learning through this input data, that is 3D point cloud from APT and 2D images from 3AM, because we want to build a user unbiased way where we can still run this code and get any data that is that gives us the real information. So with all that, now our output is shape classification and spatial distribution. So now you can see we have 3 different type of shape we could extract, which was not possible with TM and APT. TM was giving all the grayscale and APT was giving mostly ellipsoidal shape. So now with all that, this is our, another flip please. This is our final data. This gives lot of information. What are the information? That ellipsoidals are the most favorable MG clusters. So where they are formed, pyramidal. So where they are formed, there is top, middle, and bottom wave. We just wanted to understand how the lattice strain impacted the overall quip, because if there are a lot of strain, the clusters will be formed. So if the cluster distribution is homogeneous, or if it is random, or there is a pattern. So with all that classification, what we understood that cluster density increases with depth, and we see the pyramidal geometry dominates. We see other geometries like elongated and ellipsoidal, but those are minor. So that gives us a lot of information to go back to the MOCVD growth. It was MOCVD growth. So what we can do, knowing that how the layer dependent cluster formation is happening, we can change the parameters accordingly, and we can focus on what cluster is possible, also the solubility limit. So with all that, I would just summarize my talk. I know it's a lot of information, but thank you for your patience and listening to that. So what we try to do, we generate a weak data reservoir with microscopy, like a very high dimensional data and all. So instead of reduce the data and losing most of the data and having limited insights, we use AI-assisted data visualization, which gives us more like physics-informed data, like physical insights, and that we use for the material design and engineering. So just in a line that we are going from the data loss to the insight in depth. So with all that, I will thank you so much for listening to me, and I will take any questions.
Yeah, that was fascinating. A lot of it did go over our heads, I guess. It's a different domain. Any questions? So what was the application in that, the photo detector that you had?
There are different applications, but the main one here is for the defense thermal imaging.
Okay.
Because they want to see, what is, like if there are some armed faces, like you can see if there is a card on the radar. So this is mostly for that, but it is used also in medical applications. So it's basically thermal imaging with IR.
And being from computer vision, that's the one thing that caught our eye. Like, I mean, here that that's interesting. So in terms of also.
So what kind of compute resources do you require for your work? And is UB providing that kind of compute? Obviously, we don't have quantum computers and things like that, but just interested in, is this a desktop machine with a couple of GPUs in it, or do you really need huge servers?
So it depends. We use CCR sometimes. So one thing I didn't show, we are doing vacancy detection where we have really like long process and like faster processing needed. We use CCR, but some of them, some of them are CCR actually, but some of them are just our own desktop. It's a little bit powerful CPU, that's all, but we can't use regular one because we don't develop algorithm, and that's why I'm interested to collaborate with the, but we use them. Yeah, I think.
Are you thinking that maybe Empire AI will be one of the resources that you use in the future?
Actually, I missed the deadline. So there were some proposals submitted.
Yeah, no, we've been going through the same thing. So.
Because I really wanted to use, because sometimes, like even though we use the desktop, but we know the limitation, and CCR also is limited. Not always we can do things what we want. So I saw the email, but it just, sometimes, we are doing other stuff and I totally missed. But yes, that would be very helpful. And I'm looking forward for the next cycle, or I don't know when it is coming, but yeah, that would be helpful.
think we have more computer scientists in the room than material scientists, so we're interested in those aspects. And
But this
yeah.
is very helpful for us. I mean, that's why. Yeah.
So I think, we will sort of, circulate more information, and we'll see, like, if we can get some collaborations going once sort of we understand the domain aspects of it better. With the computation thing, in addition to Empire AI, there's other resources that are available, and we are trying to see how we can make some of those available as well. So I'll reach out to you.
Yeah, that I'm looking forward to, because, you see that the complexity, right? So sometimes we are limited. We are material scientists, and my background is actually physics. I ended up here, but so we are not like everywhere. We cannot do everything. We have our own limitations. So definitely the computer scientist will be very helpful for us. So
of course. Yeah, so let me just give you a token of our appreciation. Thank you very much for participating.
Thank you so much. I appreciate it. Oh.